So I hope the screen is visible in PPT mode.
Yes, ma'am.
Right. So good morning to all. The class which we have the content which we have discussed in yesterday's class, that is actually we have started distillation column. We have covered basics of distillation column, which you people are already aware, and then we have moved towards the design part of distillation column, and we also have seen the basic equation, energy and material balance equation, equilibrium relation and all. And then we have started a design of multi-component system with respect to computation of the trace to separate multi-component system. Okay, so in that connection we have discussed a specific approach, that is Henstebeck's method, which basically what we can say, it converts the multi-component problem into binary, and then it is solved using McCabe-Thiele method. Okay, McCabe-Thiele method that you have already read in your mass transfer course. So that is specifically for binary. So we will this Henstebeck's method brings the multi-component problem to binary level, and then it is that McCabe-Thiele method is applied. So this Henstebeck's method is also called as pseudo-binary method, pseudo-binary approach. Okay, so we have discussed the method completely with one example, and you know that when Henstebeck's method is considered, it basically considered limiting flow rates of all non-keys. Okay, so anyway, first of all, you need to identify the key component, and then other components are non-key with respect to light as well as heavy, right? And fixing or limiting the flow rates of non-key component, and reducing that from total flow, we can have the flow of combined keys. Okay, and then that can be solved using binary. So that is about the Henstebeck's method. Yesterday we have solved one example which we have taken directly from the book, okay, volume 6, and here I am having another example. uh, So if you see this example, it is a multi-component distillation column. Uh, the composition and relative volatilities are given. So composition of feed, top and bottom, that is given already. And if you see here, we are getting very little amount of that lighter component, even lightest component also. So if that type of situation is there, when you are not able to clearly identify where light and heavy key is occurring in the mixture. In that case, you can identify the in that case you are already aware that between which component separation is required. It means that would be known to you. Okay, so to choose light key and heavy key, either we are known, or we can have the we can identify based on the definition which we have discussed in the last class. Okay, lightest in bottom and heaviest in top. Okay, in that way we consider. But if you consider this particular table, it has component, and we have C1 to C5, and light key and heavy key are already given over here. Okay, so but it is not like always we have this light key and heavy key. You can have a separation between any two. Okay, that may be C2 and C2 and C3, or that may be C4 and C5. Okay, so in that way you can have the uh, that you can identify the light and heavy key, or uh, identification is done at in two way. One is it is already given to you, or secondly it you can obtain that from the given equation, given guideline which we have discussed in the last class, right? So here I'm having the composition of feed top and bottom, and as far as volatilities are concerned, we are given volatilities, and these are basically relative volatilities. Okay, if you see the heavy key, it is given as 1. Okay, so all relative volatilities in multi-component system we represent with respect to heavy key. Okay, so if heavy key, you can have a 1 over here, then you can figure out that this is nothing but the relative volatility. And top and bottom temperature, that is with respect to temperature, it is given. So we need to first consider the average volatilities, and what we need to do with this problem, like using Henstebeck's method, calculate slope of top and bottom operating lines. Okay, considering reflux ratio as 3. So similar problem you have done in the last class, we have discussed, but that is the example only. But here you can have another example. So first of all, we have to find out average volatilities between top and bottom. And if you see here, these volatilities are basically it is not arithmetic average, it is the geometric average. Okay, so you can consider arithmetic also, but because that difference is not much, so we can have that geometrical mean also. Okay, and once I'm having this average volatility according to each component, so you can identify that C1 and C2 would be light non-keys and C5 would be heavy non-key. Okay, so as Henstebeck's method collects the flow rates of all non-keys first, so that we will do over here, like for light non-key C1 and C2, we will have this Li should be equal to Di by L5 minus 1. So that should be what? That should be your limiting flow rates. Okay, which we have discussed in the last class. So Li you can see over like this, and similarly Vi should be Li plus Di. These expression we have already seen in the last class. So summation Li and summation Vi you can uh, consider like this, and in the similar line we will find out the limiting flow rates of heavy non-key. Okay, like C5 is given over here, and accordingly we can have Vi prime, this is not 1, this is prime, and similarly Li prime should be equal to Vi prime plus Bi prime. I should be subscript, and the instead of 1 you can consider prime. Okay, so in this way we can find out the limiting flow rate of heavy non-keys, heavy non-key component, and then we can find out the flow of the combined key. Okay, so if you see here, this is based on the similar calculation as we have considered in the last class, and these are the expression, and you can find out this easily, there is no complication. Right, so values are more or less same as the previous problem, only slight variation is there, so you can have the values in the same order, same range. Okay, so in this way you can find out that flow rate of light and heavy key, sorry, to flow rate of liquid as well as vapor in rectifying section or stripping section. And once you have this, you can find out slope of the operating line, as you can see over here, slope of the operating line, and then we can have that xb, xd and xf. And once we have this, we already know the equilibrium relation, and considering different value of x, you can have different value of y, and that x and y represent the composition of light key in liquid and vapor phase respectively. Okay, so in this way you can find out the all necessary information required to perform McCabe-Thiele method, to carry out McCabe-Thiele method. Okay, so from here onward you can have McCabe-Thiele method, and that will be after drawing the steps you can find out the number of trays. Okay, so I'm not going to discuss that you already know. So that is about the Henstebeck's method, and we can have the what we can say, the number of trays for this multi-component system. Okay, but obviously this is one distillation column. Okay, when we have the separation of light and heavy key, light and non-light, light and uh, light key component and light non-key component, those components also require distillation column, another distillation column. So in multiple component series of distillation columns are kept. Okay, or otherwise you can have the, like, whatever composition you need, composition you require, if that composition is you are finding in any tray in a distillation column, from that you can have the product as side stream. Okay, so that is mostly it is done in refinery. So that way you can do, otherwise you can have series of multi-component systems. Okay, so that is about the Henstebeck's method. Now we will consider another method, and that we call as the method for empirical correlation. If you consider Henstebeck method, what you have done, that is basically the graphical approach. How it is graphical? Because you need to draw the graph to find out number of trays. Okay, however, in this particular method we will consider empirical correlation to find out number of trays. So let's see this design of multi-component system. The method is Arber-Maddox method, or Arber-Maddox correlation. Okay, right. So this Arber-Maddox method, when we are considering, as I have told you, this is empirical correlation. Okay, but the first graph is this. So you can say that this is again the graphical approach, but no, this graph we will use to see the values only. Number of trays and other parameters we will calculate by empirical correlations. Okay, so therefore this is not the graphical approach. Some graph is required to refer. Okay, so this Arber-Maddox method completely rely on this particular graph. What this graph shows, like on x-axis I am having nm by n. Okay, nm is basically minimum number of trays. Okay, minimum number of trays divided by n. N is the actual number of trays which you need to calculate, which you need to find, right? This R by R plus 1 is the reflux ratio of the problem, which is given in the problem. Like in last problem it is 3. So R by R plus 1, where R is the reflux ratio of yes, this is reflux ratio of the problem which is already given. Okay, and thirdly we are having these lines. Okay, so these lines represent Rm by R plus Rm by Rm plus 1. So Rm is basically minimum reflux ratio. Okay, so you need to identify the minimum reflux ratio, you need to identify minimum number of trays. This is already given. Okay, so by considering the suitable line of this curve and this R and R plus 1 value, wherever it will cut this line, you can see the x-axis and nm you already know, so n you can calculate. I hope you are getting this. So in this way we can find out, first of all we need to find out nm and rm. Nm is the minimum number of trays. At what condition you will find the minimum number of trays? Okay, minimum number of trays refer to the what we can say total reflux condition. Okay, if I'm having total reflux, it means liquid is available in sufficient amount. So in that case, the number of trays would be lesser, because that liquid is available. So you will have interaction with the mass transfer with less number of trays. And you know already, na, as we are moving to increase the total reflux, the number of trays will keep on decreasing. And similarly, if I'm having least reflux ratio, minimum reflux ratio, the number of trays would be maximum. So NM we need to identify, and RM we need to identify. Okay, NM will be at total reflux, RM will be at minimum reflux condition. Okay, sorry, yes, RM is already a minimum reflux which gives the maximum number of trays. Okay, so we will find out NM as well as RM, and to calculate that, the number of when we would like to use this figure, we need to identify minimum number of trays and minimum reflux ratio, NM and RM, that we have already discussed. And that you people must have read that when total reflux condition is there, how we calculate the number of trays. The number of trays you can identify by using a very common, very well known expression, and that we call as Fenske's equation. Okay, minimum number of stages at total reflux condition. So Fenske's equation you can use, which says that this xi by xr. Okay, that is if we are considering multi-component system, that should be light key and heavy key. Okay, xr is refer component, the component to be referred, and usually in multi-component system, that reference component is nothing but the heavy key. Okay, and that is equal to alpha I nm xi by xrb. So this is for distillate, this is for bottom. Okay, and this alpha I is the relative volatility, nm number of minimum number of trays. Okay, so this is the Fenske's equation. You already have read it, I think so. You must have read that in the mass transfer course. So the parameters we have already we have already discussed over here. And uh, NM is the minimum number of stages, and alpha I, when you are considering, this is a relative volatility of ith component with respect to heavy key reference component. Okay, so this is about ith component and rth component. However, when we consider multi-component system, we first of all we need to identify light and heavy key. So light and heavy key, when we are considering, we can represent the Fenske's equation like this. Okay, you can simply rearrange this. This is simple. Like mathematics is there. So nm, that should be equal to log x lk by x hk, light key and heavy key for distillate, and this is heavy key and light key for bottom, by log lk, relative volatility of light key with respect to heavy key. Okay, so nm you can find out, there is no like complication to do this, only composition, correct composition you need to choose. Okay, so that is the minimum number of stages. Next, we need to identify minimum reflux ratio, and that minimum reflux ratio, when we consider, this is given by again a well-known equation, and that is Underwood's equation. Okay, under this probably you have not read so far. So Underwood's equation, when we are considering the expression is like this summation alpha I xid by alpha I minus theta equal to Rm plus 1. So Rm is the minimum number of, sorry, minimum reflux ratio, but that how you can identify until unless you won't consider this. So alpha I means ith component alpha. Okay, relative volatility of ith component, and xid, that is the composition of ith component in distillate. Okay, so if any problem is given to you, you are already aware of the composition of distillate as well as bottom. Okay, so XID and alpha I, everything you can you can calculate or you can find in the table. However, we are not given this theta value. Theta value again we need to calculate. Okay, so how we will find out this theta value? Theta value, for that we need again a different correlation, and that will depend on the feed condition. Like you must have remembered this Q line. Okay, so that Q line should be what we can say equal to 1 when we are dealing with boiling condition. Okay. So the expression is like summation alpha I xif by alpha I minus theta, and that is equal to 1 minus q. Okay, so in from this you can find out this theta, but the thing is whatever q value is there, that you can it decides the right hand of this equation. However, this is basically the summation of each component. Okay, so you can keep on adding this, like for first component, that is alpha 1 x1 f by alpha 1 minus theta plus alpha 2 x2 f by alpha 2 minus theta. In this way, whatever would be the number of components in that, so many terms will be available with theta. So that theta you need to choose in such a way so that the whole equation should be satisfied. So that would be done by trial and error, or simply if you can have the equation solving that you can solve the equation through calculator directly, so that theta you can find out directly. Fine. And here also you should understand that this theta, when we are considering, let's say I'm having 5 component or 3 or let's say 4 component in feed. Okay, so 4 terms of theta will be there. I hope you are getting my point. If I'm having 4 different components in feed, I'm having 4 different terms of this expression, and I'm having 4 different what we can say. If we will solve this, we will find out 4 different values of theta, right? But here only one value you need to choose, and that value would be which is falling between relative volatility of light key and heavy key. Okay, theta correct value should fall between relative volatility of light key and heavy key, and whatever that value is, that you need to choose to find out this uh, to use in this particular expression, and to calculate uh, to find out theta, sorry. Huh? So that theta value, once you identify between relative volatility of light key and heavy key, you can use this equation to find out Rm. Okay, and once you have the Rm and Nm, you can use the graph. Okay, so the only problem over here is to this equation and this equation. Otherwise, method is very simple. Okay. So here we will discuss some like factors, or we can say the example of this Erber-Maddox method, and it is again from the book directly. Okay, so no, what we can say, no variation is required than the example given in the book. So I have taken the same as it is. So here for the following separation, estimate the effect of changes in reflux ratio on number of stages required using Erber-Maddox method, and feed is available at boiling condition. Okay. So here I'm having I think this is the same problem, and here light key and heavy key we have identified, but you can see a little bit composition is already available. Okay, so that you can consider as it is. Okay, so if this is the situation, you will be known that between which component separation is required, and so you can choose light key and heavy key accordingly. Okay. Right. So let's start this Arbor-Maddox method. The first step over here is to find out the minimum number of stages using Fenske's equation. Okay, just a moment. Right. So Fenske's equation we will consider over here to find out minimum number of stages, and that this is given to you. Okay, and that nm you need to identify x lk uh, x hk for distillate, that you can identify from here. Nothing, it is not complicated. This is feed for feed, so this is 24 by 1. Okay, in distillate. 24 by 1, you can see over here 19.19 by 1 by log 2, that is relative volatility of light key with respect to heavy key, as you can see over here. Okay, wherever this heavy key 1 is given, okay, you should understand that is relative volatility, otherwise it is not. Okay. So number of stages, considering all these parameters, we can find as 8.8, and next is to find out the minimum reflux ratio using Underwood's equation, and this minimum number of stages that is given as 8.8. What does it mean? These are the minimum number of stages only for calculation purpose. You don't need to round off or round up this. Okay, whatever is coming, that you need to consider as it is, because that will be further utilized. Okay, to calculate actual number of stages. So this nm should be the for calculation purpose only. Okay, so in that way you can find out, you can consider nm, and Underwood's equation minimum reflux ratio we need to find out considering this equation, and feed is at boiling point, so q quality, or we can say q should be 1. Okay, once I'm having this Underwood's equation, we need to find out Rm, but before that we need to calculate this theta. Okay, so theta, when I'm considering, if it is at boiling condition, the expression should be equal to 0. And you can see over here I'm having xf. Okay, xf, different xf's are already given. uh, Alpha I, that is given over here. Okay, so alpha I is given over here, and we need to find out theta. So theta, you need to see, there are two different ways. One is, as I have told you, you need to consider all these expression. Just a moment, please. we are given this table. So what I was saying that theta you can find out by two way. One is if you collect this term with theta, like I'm having five different components over here. So for this summation term, you will have five different terms in which theta, in each term theta will be available, and that should be equated to 0. That is one way that you can directly solve that equation with all five terms and find out theta directly from the calculator. And secondly, you can have you can assume theta value and then you start computing. Okay, so what is the guideline to assume this theta value? As I have told you that correct theta value will be found between relative volatility of light key and heavy key. So here between 1 or 2 the value should lie. Okay, so we will start with 1.5, and considering these term theta value 1.5, we can get the final summation, and you can see we keep on iterating till I'm getting theta value close to 0. Okay, so in that way theta value 1.35 you can find out, 1.35 you can consider. Okay, so in that way you can choose the initial guess for theta, and considering different values of theta, but uh, that value of theta should be between light key and heavy key relative volatility. Okay, and then after few iteration you can get the value of theta as you can see over here. Otherwise directly you can put that in the calculator and solve that, but in that case if five components are there, five different values of theta you will obtain. So correct value should be between these two, right? And that would be only one value, only one value theta value. If you see between 1 and 2, that the variation is significant. Okay, so in that way you can find out theta. Once I'm having the theta, half of the problem you have done already. So this is the expression of Underwood's equation, where this term is equated to Rm plus 1, that is minimum reflux ratio. So XD I already given to you. Okay, when you consider this XID, you are basically given the total flow. Okay, but I think you can calculate mass fraction. Okay, XID is the mass fraction. Similarly, XIF is the mass fraction. So before proceeding further, you need to find out fractions from the total. Okay, so alpha I is given, then alpha I xid it is given, so we can put the values in this expression and take the summation. So that should be 2.42 and theta should be 1.35, that we have just discussed. So Rm plus 1 should be 2.42, Rm 1.42, and in the graph Rm by Rm plus 1 is given, so that should be 0.6 around. Okay, and reflux ratio if you consider 2, okay, so that should be 0.66. okay, so we can use this graph. So Rm by Rm plus 1.6 it is given 0.59, so you can have this particular curve. Okay, and R by R plus 1.66, 0.66, so 0.6 and 6 or somewhere over here. So you can take the value like this. Okay, wherever it will cut this line. I hope you are getting this. And 0.6, okay, 0.66 should be here. Okay, and once you consider this point, it is coming as 0.56 nm by n. Okay, because on x-axis I am having nm by n, so that value you can find out, and then n should be nm you have already calculated 8.8 by this n, so 15 by 0.6 should be the number of trays. Now this number of trays you need to round off, sorry, round up. Okay, so this final n you should consider in like complete number in but not this nm. Okay, nm may remain in decimals. Okay, so in this way you can find out, you can consider Arber-Maddox method to find out number of trays using analytical or empirical correlation based approach. Okay, so another example we are considering is this is the same example, and here I am having reflux ratio as 3. So light key and heavy key, that is already you are aware of. So here I am having this these components, and this nm you can find out, nothing it's not complicated. It is basically the same example, only with slight variation in the values. Okay, so almost same type of thing you will find. So nm it is coming as 8.7, and this alpha I xif xi, if you see this, these are 5 component. So if you see, if you would like to find out theta, that term should be equated to 0, and I'm having 5 different terms of theta, as you can see over here, like this. Okay, and if you see, instead of fraction we have directly considered the mass. Okay, as you can see over here that for feed this is 5, 15, 30, but here it is it's divided by the total mass flow. Okay, so this is nothing but the fraction only, right? So we will have 5 different values of theta, and when you solve this equation directly in calculator, you can find out theta value as 1.274, and that other values are also there, but you will choose this value as it is lying between relative volatility of light key and heavy key, right? So in that way you can find out theta. Once you have this theta value, you can find out this you can find out the rm, expanding this particular term. Okay, and here you see we have considered fractions. Okay, not the flow. So rm you can find out like this. So rm by rm plus 1 you can find as 0.58, and r is given as 3, so that is 0.75. Again, from the nm by n you can see the value 0.75 should be here, and that value should be 0.58, 0.6, somewhere here it will lie. So you can see the value from the graph. There is it's not complicated, and once you do this you can calculate number of trays, and then you have to round up the number of trays, actual number of trays. Okay, so in this way you can consider Arber-Maddox method to find out the number of trays. Okay, so multi-component system, a number of trays we can find using Henstedt method, or as well as Arber-Maddox method, in anything you can use. Okay, and now we will proceed towards another topic, and that is plate efficiency. Okay, just in 1 minute I'll start. Yes. So now we will start another topic in this distillation column design, and that is plate efficiency. A few, or we can say prelim of this plate efficiency, you have already you must have read already in your mass transfer course. And when we consider this efficiency, plate efficiency, why it is important? Okay, because when we calculate the number of trays from any method like McCabe-Thiele, Henstedt-Bex, Erber-Maddox, whatever method we consider, it gives us the ideal number of trays. Okay, or the it consider the that what we can say, the separation is as per that requirement. Okay, so that separation is per what we can say complete, and because of that we have the ideal number of stages. But in actual sense it is not the case. We need to consider, we need to see whether the actual separation we would like to have, that we are getting or not. Okay, so equilibrium will rely rarely be attained in real stage. Okay, the concept of stage efficiency is used to link the performance of practical contacting stages to theoretical equilibrium stages. Okay, so if you consider this stage efficiency, that is what exactly separation we obtain and what we are expected to. Okay, so that you can see when we when we make the steps to find out number of trays, every time we used to touch this point and then this point and then this point. Okay, but if I consider this as well as this, okay, that is the real, or that is the what we can say, the ideal enrichment we expect. Okay, but in actual sense we reach up to enrichment point B only, not point A. Okay, so the stage efficiency, that is BC by AC. Okay, and that we define by that has been defined by the Murphree, and therefore it is called as Murphree plate efficiency. Okay, so Murphree plate efficiency is the ratio of actual separation achieved to that which would be achieved in an equilibrium stage. Okay, so that Murphree plate efficiency should be it is equated to y minus yn minus 1 divided by ye minus yn minus 1 parameters that you can you are already aware of, where ye is the composition of vapor that would be in equilibrium with the liquid leaving the plate. Okay, so in that way you can find out the Murphree plate efficiency, but that is very, what we can say, the um, very simple definition. Okay, however it's not it only depends on the separation, it depends on different other parameters also. Okay, or we can say more mass transfer characteristics we need to consider before deciding this before deciding this plate efficiency. But this is the definition of Murphree plate efficiency that you know already. Okay, so this is Murphree plate efficiency. Okay, another efficiency we are having is Murphree point efficiency. Point efficiency, you understand, over the plate at a particular point, whatever would be the concentrations that we consider as the what we can say, to find out Murphree point efficiency. Okay, if the vapor and liquid composition are taken at a point on the plate above equation which gives the local or point efficiency. Overall column efficiency, that you can all see that we have the what we can say, ideal trace by real trace. Okay, some what division of these two will give the overall column efficiency. So these three definition you have read so far. Okay, now we will build over it. Okay, now we have a few correlations, few approaches through which you can find out the you can find out the efficiency. So this first approach is the O'Connell approach, or we can say the O'Connell's correlation. And this correlation calculates the overall column efficiency. Okay, column efficiency, it's not you are given ideal number of trays and you are given real number of trays. If that those trays are not given to you, so what you can do, you can calculate column efficiency by this. If you are already know the ideal number of trays, you can find out the real number of trays, okay, using expression this expression, right? So this O'Connell's method, it gives the column efficiency overall, and that is very simple method, quick estimation. It says that the overall column efficiency is correlated with the product of relative volatility of light key component. Okay, product of relative volatility of light key component with respect to heavy key, of course, and the molar average viscosity. So alpha and mu of the feed, okay, that you need to consider, and this should be at average column temperature, this viscosity. Okay, and that relative volatility also. Okay, so here 2 points, two parameters are there. One is relative volatility, okay, second is the average viscosity. Okay, and relative volatility of light key, but average viscosity of the feed. Okay, so this is the graph, and we have this equation also just representing this graph, nothing else. Okay, this curve. Okay, so here I am having alpha A and mu A. Mu A is the average viscosity of feed, alpha A relative volatility of light key with respect to heavy key. E naught we are having as the column efficiency. Okay, so you need to calculate this first and then you see the graph, or you can directly calculate from this equation, no problem. Okay, but this is a quick estimation of overall column efficiency. Okay, this is the nomenclature, nothing else. Okay, so let's see the example. This example also I have taken from the book directly, and it is like O'Connell's correlation we need to use to find out overall column efficiency required for the separation which is given. Okay. So this is the compo flow of the components which is given over here. Okay, this is the same example, and column top temperature is 65, bottom is 120. The average term at average temperature viscosities are given like propane, uh, it is given like this, then butane, and then pentane. Okay, and that we need to consider for the feed, right? Average viscosity, when we consider, this is like 2 is given for light key with respect to heavy key, that you can see. So alpha A is 2, we need to find out mu A. Okay, so feed composition for molar average viscosity that you can find, this is for propane into 0.05. You can see over here it is not complicated, 0.05 into this, and butane you need to add these 2.15 plus 0.25 into this. Similarly for pentane, so that you need to consider over here 0.13 meter Newton second per meter square is the viscosity. It's not meter, it is millinewton. Okay, and in this way you can find out alpha A mu A, and you can see the column efficiency from here, and that you can find out as 70%. Okay, so that you can see. Or you can use the equation also that we have discussed for O'Connell's method. Okay, now another very important parameter to find out the plate efficiency is the AICHE method. Okay, uh, that AICHE you all aware of, that is American Institute of Chemical Engineering, Chemical Engineers. So AICHE has given the detailed method to find out the to find out the plate efficiency, and not only separation, it considers many more parameters. Okay, so this AICHE method is most detailed method for predicting plate efficiency. It takes into account all the major factors that are known to affect plate efficiency. Okay, so what factors it counts? Number one, the mass transfer characteristics of liquid and vapor phases. Okay, not only concentrations. Okay, sorry, not only mass fractions. Why? Okay, but mass transfer characteristics also, and uh, mass transfer characteristics means what? Like the separate the concentration when we consider, or we can have the diffusivity, or we can in combination, when we consider mass transfer characteristic, that is that number of what we can say, the gas phase unit and the liquid phase units. Okay, that we that you must have read in mass transfer course. Okay, so that we will use over here to consider the mass transfer characteristic between liquid as well as vapor. Design parameters of plate. Okay, what is the size plate size and other geometrical parameter related to plate, that we will see. Okay, what these parameters are, that we will consider, that we will discuss. Okay, thirdly, vapor and liquid flow rates, that is the important parameter. And fourth point is degree of mixing on the plate, that is very important parameter. Okay, degree of mixing we need to find out. So based on all these parameters, the AICHE method is given. So let's discuss that AICHE method. So the mass transfer resistances in vapor and liquid phases are expressed in terms of number of transfer units. So Ng and NL, that I was uh, talking about in previous slide. So the mass transfer characteristics we can have with respect to Ng and NL, number of transfer units. Okay, in gas phase and liquid phase. Okay, so number of transfer units that you have that you must have read in mass transfer, I guess. Yes, yes, it is there. Okay, here first of all we will find out the point efficiency, and then we will proceed toward then we will calculate the plate efficiency. Okay, so the empirical correlation given over here is the point efficiency, which is EMV. Okay, and this V should be small for this point efficiency. If this V is capital, that is represented as plate efficiency. So please keep that in mind. Small v point efficiency, capital V plate efficiency. So 1 by ln 1 minus EMV, that is equal to minus 1 by Ng, that is the number of transfer unit in gas phase, plus MV by L into 1 by NL. So that is the number of transfer unit in liquid phase. N is the equilibrium at a particular point, because this is a point efficiency. V and L are the flow rates of vapor as well as liquid. Okay, so M is the slope of the equilibrium line, and that slope keeps on moving with respect to the concentration, right? That you can see in graph, respective graphs like Michelson graph and all. Okay, so once we are having this M as a equilibrium slope, equivalent line slope, V and L are the vapor and liquid molar flow rate. So we will find out first of all Ng and NL, and then we can calculate EMV. Okay. So number of transfer unit for gas phase, when you are considering, the expression is given like this. And we will see different parameters available over here. So the first one is the HW, that is weir height. Okay, and weir height, I think yesterday I have shown that to you. What is weir height? That is how much liquid can be available over the plate. So if you see this particular height, okay, and this particular height, okay, this is called as the weir height. Just above the tray, this height is given, and that is nothing but the weir height. Okay, this is downcomer section, and this weir height ensures the how much liquid will be available over the plate, right? So that is HW. This is the design parameter. We will discuss how to choose this. Where we were here, right? So HW you can find out as weir height. Okay, I have already told you this. FW is the column vapor factor. FW is column vapor. F factor. This is simply given a name, and that is equated to UA by UA into square root of vapor density. Okay, and UA, if you are considering, that is vapor velocity based on active tray area. Okay, actually when we are considering the let me show you in the same slide, just one moment. Okay, so if you consider, this is the weir height, right? Okay, now what will happen in this, that this is the plate, and liquid is coming from the top or from above plate, and it will stay over here, then it will move in this way. Okay, so if you consider, holes are available in between this line, uh, sorry. Okay, so between here to here, what we can say, holes are available. Okay, so that is from inlet downcomer to outlet weir, right? Inlet downcomer to outlet weir, and this area, whatever we are considering, that we call as the active area or bubbling area, where bubbles can be formed, and where bubble will be formed through where the vapor will be available. Vapor will not be available in downcomer section. Okay, however, vapor will pass through these holes, and it will contact the liquid and have the bubbles. Okay, and uh, this, therefore this section is called as the active area, or we can say bubbling area, where mass transfer is possible, right? Where mass transfer is possible. I hope it is clear to you. Yes. Right, so in this way you can have this UA, that is the vapor velocity based on active tray area. So if I ask you, in this cross section, active tray area should be what? This is the inlet downcomer, and that is outlet weir. Here I am showing two plates which are available one over another. Okay, this is not the single plate. Okay, so active area over the plate should be this area. Okay, that is if I consider one plate, it will be like this only. Okay, this cut will be there. For second plate, this cut should be there. Okay, so single plate has only this much area which we consider as the area where mass transfer is possible, where interaction between liquid and vapor is possible, and therefore it is called as the active area. Okay, so how to find this active area? You already know the diameter of the column. Okay, so cross sectional area of the column you already know, and this is downcomer. Okay, two downcomers areas are there. So downcomers are usually given in percentage, like 12% of cross sectional area, something like that. I will discuss that in detail in design. Okay, but given that downcomer area, twice of that when you deduct from cross sectional area, you can calculate the active area. So vapor velocity based on active area, it means vapor mass flow is given to you, volumetric flow you can find out, divide that by this active area. And how to find active area, that I have already told you. Okay, so in this way you can find out this UA. Once you have this UA, you can find out this FV. And second, and another parameter I'm having is LP. LP is the volumetric liquid flow across the plate. Just try and understand that liquid from above plate, liquid will fall in this region where no hole is available, and then it will start moving towards this direction, and from here it goes down. I hope you are getting this. So the volumetric liquid flow rate across the plate divided by average width of the plate. Average width of the plate is, if you consider this plate, this section and this section, this is quite curved sections. Okay, but average plate width we are considering, this is nothing but this. Sorry, this is nothing but this section. This section. Okay, this section. So average height we need to, or average width I need to consider, because when liquid is moving, it is moving from here to here, right? It is moving from here to here, that is from inlet downcomer to outlet wear. Okay, so the average width, that is this vertical average width of the plate, this can be calculated by dividing average area of area, not average, sorry, active area by length of the liquid path. Active area, that you can find out, that we have discussed, that column cross sectional area minus twice of downcomer area, that is active area, right? That is divided by the length of the liquid path. Length of the liquid path means from inlet downcomer to outlet wear. Okay, means distance this distance from wherever you will find, it will same. So this active area divided by this uh, length, it gives me the average width of the plate. Okay, average width, why we are considering, because here width is less, here width is highest, so we need to find out average width. Okay, now the question is how to find this ZL. Okay, because you already know the column diameter, right? And this particular gap, you can find out once you fix the downcomer area. Okay, how, that we will discuss. Okay, but you already you can calculate this part. Okay, so column diameter minus twice of this part will give ZL, right? Geometry you can apply, it's not very complicated. So once you have the ZL, active area by ZL will give you the average width of the plate, and this LP is the volumetric flow rate across the plate, and that is volumetric flow of the liquid, that you know already, divided by the average width. Okay, so in this way you can find out P, and these are some of the properties like diffusivity, viscosity, density. So all these we need to consider to find out uh, this Ng. Okay, once I'm having this Ng, we can find out NL. you can use this sorry, we can find out NL using this particular expression, where DL is the liquid phase diffusivity. Okay, gas phase diffusivity we have already seen, already considered over here, like this. Okay, now gas phase diffusivity, when we are, sorry, liquid phase diffusivity, we can consider over here FV we have already calculated. Now TL is the liquid contact time over the plate, and that is given by this ZC by ZC into ZL by LP. Okay, ZC ZL by LP. ZL, you know, liquid length, length of the liquid path. LP we have already seen, volumetric flow of the liquid by ZL. Sorry, by average width. Sorry, this LP should be volumetric liquid flow rate by average width, right? And ZC is the liquid hold up. Okay, ZL is length of the liquid path from inlet downcomer to outlet weir, and ZC, when I am considering, ZC should be liquid hold up on the plate, that is meter cube per meter square active area. Okay, liquid hold up on the plate, and that liquid hold up will depend on the type of plate. Okay, as we have change in geometry over the change in geometry of the plate, we can have different what we can say, we can have different ZC value. Okay, so in just 1 minute I will start. Okay, I'm sorry for the interruption. Okay, so once we have this uh, ZL and ZC, I will tell you that how this ZC will be calculated depending upon the type of plate. And once I'm having this NG and NL, we can use this graph. Okay, either we use this graph, this is NG and NL is available over here, to find out point efficiency. So you can use this graph also, or this equation as well. Okay, this equation is already plotted over here. Okay, so you can use, but if choice is given, I will recommend to use the equation. It will give you the correct value. Okay, graphical approach may have a little bit error. Okay, so here we need to find out ZC, that is liquid hold up over the plate. And as I have told you, it depends on the type of plate. So we will have bubble cap plates and sieve plates. Okay, I don't know whether you know these plates or not, but that we will cover in this that in subsequent lectures. Okay, what is sieve plate, bubble cap plate, and there is another plate which we call as wall plate or wall tray. So ZC, you can see, depending upon the geometry of each plate, liquid hold up will be calculated. How much HW wear height, that is like common, that may be common to all, but other parameters like active area and average width and all, that may vary depending upon the geometry. So whatever plate is given to you, to find out the efficiency, that you can see from here. And once you have this ZC, you can have NG and NL, so you can find you can calculate point efficiency, and these graphs are correlating point efficiency with plate efficiency. Okay, you see here small v is given for point and capital V is given for plate. Okay, that I have already told you. So you can use these graphs. So the graphs, two graphs are same, and here MV by LEMV, that corresponding to this, you need to see the corresponding line, and that line will depend on this number, that is PE, which is equal to Packlet number. Okay, depending upon the this value and depending upon this curve, you can find out the ratio of EMV by EMV. EMV you have already calculated, so you can calculate point efficiency easily, sorry, plate efficiency easily. Okay, so now the point is how to consider this uh, PE, that is Packlet number. It varies from 0 to infinite. Okay, so we need to consider the Packlet number, and which is defined like this: ZL square by DE into TL. Okay, ZL square, length of the liquid path, that we have already calculated. DE is the important parameter, and that is eddy diffusivity. Okay, eddy diffusivity, like eddies are formed when the mixing is there. Okay, so this basically, this factor counts the degree of mixing. Okay, the fourth point, which is considered by AICHE method, you can refer the previous slides. Okay, so we have DE, that is eddy diffusivity, and we can find out the Packlet number. If this eddy diffusivity is 0, it means no mixing is there. So in that case Packlet number should be infinite. Okay, and if this is infinite, it means perfect mixing is there. Okay, so eddy diffusivity you can find using this expression for the plate, and in this way you can find out the all parameters to find out plate efficiency from the graph. So I hope that you can do, and now we will see one example to illustrate this AICHE method. Okay, so the problem is like, we need to calculate the sieve plate efficiency located in stripping sections using AICHE method for following data. That is minimum vapor flow rate, it is given as 300 kilomole per hour, minimum liquid flow rate 900 kilomole per hour, and column diameter 0.8 it is given. Downcomer area 12% of column area. Okay, it is given over here, and that you can consider. Liquid composition, that is 10% mole, where slope of equilibrium line is given as 3. As I have told you that slope of equilibrium line vary with respect to the concentration. So here it is m value is given as 3, slope of the equilibrium line is given as 3. Okay, and wear height is given as 50 mm. Actually all these parameters are fixed over here, okay, because you have not still read the detailed design of the distillation column. Once you will read this, all these parameter you need to decide on your own, okay. But so far that is not discussed in the class, so I am giving all these values, okay. Liquid and vapor properties are given, like molecular weight and all, because here molar flow is given, okay. So in this way you can find out this uh, you can have these properties, and then you can calculate the sieve plate efficiency. So plate type is already fixed over here, that is sieve plate, okay. So let's start the calculation. First of all, we need to find out Ng, and for Ng, we need to consider the weir height. Weir height is 50 mm, it is already given. We need to find out Fv, and for Fv, we need to find out UA, okay. And to find out UA, we have to consider active area. So first of all, we will find out active area, that is column area minus twice of downcomer area, because both side downcomer is there, okay. So this column area we can find out, column diameter we are already given, so we can find out column area as 0.5024. We can calculate active area, okay. So 12% AC, this AC should be beside this, A capital and C subscript, as you can see over here, okay. So this column area into 0.76 would be the active area, okay, and that is coming as 0.382 meter square, okay. Weir height, when I'm considering, that is 50 mm, we have already discussed. Now next we need to find out ZL, because ZL is required to find out capital LP, okay. So ZL is basically length of the liquid path, and that is from what we can say, inlet downcomer to outlet weir, okay. So that is column diameter minus 2 LH. What is this LH? This is the LH, okay. If you consider, this is LH and this is LH, so column diameter minus twice of this LH will give you the ZL. ZL is this, remember? Yes, okay. So coming back to this slide, so 2 minus LH, actually this LH will depend on the downcomer area, okay. How much cut will be there, depending upon this LH value will be decided. So for now you consider the LH value as 0.144, okay, for now also, only. Otherwise that value we will discuss in future slides, or we can say the subsequent slides, okay. So till then you can consider LH as 0.144, okay. And twice of this LH that we can deduct from column diameter, so length of the liquid path is coming as 0.152, okay. Length of the liquid path is 0.152, okay. So average width over the plate, that is active area by ZL. Active area we can find by this, and ZL, sorry, I think it should be 0.512, not 0.152. Just let me check it. Yes, it is 0.512, okay. So please make a correction over here, this is not 0.152, this is 0.512, and 0.512 we can consider over here to find out average width, which is coming as 0.746, okay. And then we can find out LP, that is liquid volumetric flow rate by average width, okay. So that you can find out, first of all you need to find out volumetric flow, because molar flow is given. Considering that molecular weight, you can find out this you can find out this liquid volumetric flow, and LP it is given over here. Sorry, LP you can calculate like this, which is coming as 7.649 10 to the minus 3. So in this way all parameter you can decide, so you can find out number of transfer unit in gas phase. Okay, transfer units in gas phase, and this is the expression, and you can calculate all parameters FV and all. So for FV UA is required, so that you can identify, and FV is coming as 6.523. Okay, so all parameters we know already. So Ng number of transfer unit is gas phase is coming as 0.3856. Okay, so next is to find out NL, and for that NL you need ZC, ZL and TL. Okay, so ZL you already know, ZC you need to identify, that is liquid hold up, and when you consider the liquid hold up, given the value, you will find the value of ZC as negative. Okay, so here the infeasibility is there. It means some parameters we have defined in wrong way, and so this liquid hold up is coming as negative, though it cannot be. Liquid hold up should always be positive, okay, not negative. Okay, so here the problem is becomes infeasible, so we cannot proceed with this value of ZC. So for calculation purpose only, to illustrate the example further, I have taken this ZC as 0.019. Okay, TL you can find out by this ZC ZL by LP, so it is coming as 0.127. Okay, and then you can find out number of transfer unit in liquid phase. Expression is given already, values you know already. So NL is coming as 2.6642. Okay, and NG is coming as 0.3856. Now once you are having this NG and NL, you can find out that point efficiency, right? And uh, after point efficiency, you will be required to calculate plate efficiency, for which Peclet number is required, and for this eddy diffusivity is required. So this is the expression for eddy diffusivity we just have discussed, and then you can find out Peclet number as 10.97. Okay, so here actually it is, I think, it is 10%. Yes, 10%, and slope is 3. So some variation you can have over here, like this slope of equilibrium line, that should be 3, that should not be 2, which we have considered over here. Please make the correction over here and revise the calculations. VNL that is given to us, that we can have the ratio of this, so MV by L that you can see, and this MV by L by NL, that is that you can calculate, which is coming as 0.25, and that you can put over here 1 by that NG value you already know, so you can find out point efficiency as EMV, which is coming out as 0.296. Okay, now once I'm having this EMV, okay, EMV, we need to consider this particular parameter MV by L into EMV, and Peclet number 10.9 you have already seen. Okay, so you can find out this MV by L into EMV, and which is coming out as 0.1974, and 0.1974, if you consider, it will be very near to this point. Okay, however 10 point would be somewhere like this. So it will be available here. Okay, so you can find out EMV by EMV, that is, you can see from the graph, which is coming as 1.08, and you can find out using this ratio, you can find out plate efficiency, which is coming out as around 32%. Okay, but here the calculation you need to change with slope 2, with slope 3. Okay, so that you can consider, but the procedure, I hope it is clear to you. In this way you can find out the that plate efficiency, and related to that one example is already given in the book. So I request you to calculate or solve that example also. So that is about the plate efficiency. That topic is over now, and we will consider the we will extend the discussion further in the next class, probably tomorrow's class. Okay, so that's all from my side for today. If you have any confusion, any observation, you can share. Okay, so that's all from my side for today. So if you have any query, you please discuss.
Hello.
Yes, yes, Anish, tell me.
Ma'am, we have to follow the same pattern in the CET one, or we have followed the theory two, ma'am, for this course.
Sorry, please
We have
be loud.
we have to concentrate on the numerical only, or we have to follow on the theory portion, ma'am, too.
Actually, this theory, if you see the theory, that is only for the design part, right? Right. Nothing we need to, nothing we have derived. Empirical correlations are there. So theory is only to understand.